Today we will discuss the concept of continuous function. Now this is a very important concept of continuity of function. Now first of all, how do you define a continuous function? In common term, in layman terms, by continuous function we mean a function which can be drawn, or the graph of that function can be drawn in one motion without picking up your pencil. For example, suppose I am drawing the graph of a function like this, then this function is continuous from here to here. But suppose I have been given another graph of a function like something like this, then this function I cannot draw without lifting my pencil at this point. So this function, the second function, is discontinuous function, that it is not continuous, and the first function is continuous from here to here, this point to this point. Now this is very simple definition in layman terms, and this definition uses geometrical concept of drawing a function. Now how do you mathematically define the concept of continuity of a function at a point? A function fx is continuous at an interior point of domain. Now I am considering myself, now I am considering an interior point of the domain, that is domain of the function is given. Now I am picking up any interior point of the domain and finding out what is the condition so that I can say that this function is continuous at that interior point. Now there are three conditions. If the function meets three conditions, I will say that it is a continuous function. Number one, it has to be defined at that point, so fc has to exist. Number two, limit x tends to c, fx exists, that is the limit of the function should exist at that point c. And the third condition is that the value of function and the value of this limit should be equal. These are the three conditions under which a function will be said to be continuous at an interior point x is equal to c. Function is continuous on an interval if and only if it is continuous at every point of the interval. The same thing I am explaining using a graph. So suppose this is the graph of my function y is equal to fx. If I have to check continuity at this point c, then first of all, the function has to be defined at c, that is fc has to exist. So this is number one condition. Number two is that the limit of this function at x is equal to c has to exist. Now for limit to exist, we had seen in previous lecture that the limit of a function will exist at a point if and only if the right hand limit and left hand limit both exist and both are equal, that is limit x tends to c plus the right hand limit fx is equal to limit x tends to c minus the left hand limit. So in this case also you see the red arrow shows the right hand limit, so the right hand limit, the blue arrow is showing the left hand limit, so these two limits have to be equal. Okay, and the third condition is these two limits have to be equal and they have to be equal to value of function at that point, that is fc. So when these three things are equal, that is fc, right hand limit and left hand limit at that point c, then we say that that function is continuous at that point, at that interior point c. Now what will happen? Suppose I have to find at an end point like this, a is an end point, b is an end point of the function. So at that end point we say we have to check whether the function is continuous at a left end point, say a, if your right hand limit, that this thing, and the value of the function fa, they are equal. Similarly, if I have to check continuity at this point, right end point, that is b, I will check whether this limit, that is the left hand limit at b, is equal to value of function at b. So this is the definition of continuity at a point and continuity at the left end points and the right end point. Similarly, you can say that a function f is right continuous, that is continuous from the right at a point x is equal to c in its domain if the right hand limit is equal to fc, and then it is left continuous, that is continuous from the left at c if left hand limit is equal to FC. See some examples of graphs of function and check whether the function is continuous or not. Suppose this is my function y is equal to fx. I have to check whether the function is continuous at this point or not. Simple, the value of function is also given by this dot, and the right hand limit also. Right hand limit will be from this side 1, left hand limit will be 1, so this function is continuous. Okay. Now what about this function? You can say that this function has got limit. The right hand limit also, as you approach from right, it is 1. Left hand limit is also 1, but the value of function at x is equal to c has not been defined, because you see at 1 there is a vacant slot, there is a vacancy. So f of 1 is not defined, so this function is not continuous. Okay. Similarly, you see this function. In this case also, right hand limit and left hand limit, these two are equal, but the value of function at x is equal to 0 is equal to 2. So the right hand limit is equal to left hand limit is equal to 1, but f of 0 is equal to 2. So this function also is not defined at x is equal to 0. Okay. Now see this function. In this function the left hand limit is 0, right hand limit is 1. So obviously the limit does not exist. Limit does not exist. So this will also be not continuous, because for continuity the limit has to exist. You see this function here also, the left hand limit is going to infinity, right hand limit is also going to infinity, but the function is not defined, because at x is equal to 0, 1 by x square is not defined. So this is also not continuous. You see this function. In this case we had seen in previous lecture that the limit does not exist, because this function sine 1 by x is oscillating very vigorously. So this limit does not exist, so this function is also not continuous. So we have seen that in this case only this function is continuous at x is equal to 0. In this case the function is not defined at x is equal to 0, so it is not continuous. In this case also it is not continuous, and similarly the remaining cases also the function is not continuous. But in these two cases there is one possibility, that if I suitably defined my value of function fx, then I can make these functions continuous. How? You see, in this case if I define my f0 is equal to 1, if I give this definition to my function, then what will happen? This dot will be filled and my function will become continuous. There was a gap here. You see, this gap was there. Once I fill this dot by defining my function as f0 is equal to 1, this gap is filled. Now my function is continuous. Similarly, in this case, the right hand limit and the left hand limit both are 1, but this function was defined as f0 is equal to 2. So if I change the definition of this function and make my f0 is equal to 1, that is, I define f0 is equal to 1 here, then what will happen? This function will also become continuous. So these kind of discontinuities, basically they are given as discontinuous function, but the discontinuity can be removed by suitably defining the function in a suitable way. So such discontinuities are called removable, because they can be removed. So I will call them removable discontinuity, because they can be removed by suitably defining your function. Okay, but what about these discontinuities? This function and this function, they cannot be removed. Why? Because the function has got a jump here. So no matter how you define your function, ultimately this left hand limit will not be equal to right hand limit. Similarly, in this case at x is equal to 0, this is the function, the value of function does not exist. In this case also the function is oscillating so furiously, the function is oscillating so vigorously that the limit does not exist. So these three cases, D, E and F, the limit, the function cannot be made continuous by any trick or by any suitable definition of function. So these are non-removable discontinuities. Okay, so these two are removable discontinuity, but these three are non-removable discontinuity. I can define a continuous function in a related way like this also. A function is continuous at a point if the limit is the same as the value of the function. Why? Because we had seen that a function is continuous at a number a, it is continuous at this number a if and only if the limit x tends to a fx, that is that limit fx is equal to fa. So the three conditions are same, that is the function fa has to be defined and this limit has to exist and this limit is equal to f of a. Now you can see in this graph, suppose my function y is equal to fx is defined at like this, then this function has discontinuities at x is equal to 1. Why at x is equal to 1? Because you see at x is equal to 1 your left hand limit is this thing, it is going to 1, right hand limit is this, so left hand limit is not equal to right hand limit, so the limit does not exist, function will not be defined. It will also have discontinuity at x is equal to 2. Why? Because you see at x is equal to 2, although the right hand limit and the left hand limit both are equal to 1, so limit x tends to f of x is equal to 1, that is the function has got a limit at x is equal to 2, but the value of the function at x is equal to 2, this is 2, this is my f of 2, so f of 2 is not equal to limit x tends to f of x, therefore it is not continuous at x is equal to 2. Okay, so these are the two discontinuities. But you see about x is equal to 1, at x is equal to 1 the value of function is also 1 and the right hand limit also is 1, so it is continuous. Remember, this x is equal to 0 is my left end point because my function is defined only till x is equal to 0. So at left end point what we check value of function and the right hand limit. Similarly you see at x is equal to 4, at x is equal to 4 the left hand limit is equal to 1 and the value of function is also equal to 1, so it is continuous at x is equal to 4 also, because the one-sided limits match the value of the function. So this function has discontinuity at x is equal to 1 and at x is equal to 2, and it is continuous at x is equal to 0 and x is equal to 4. At x is equal to 1, this discontinuity, that is x is equal to 1, whether it is removable or non-removable, it is non-removable discontinuity. Why? It is non-removable because you see at x is equal to 1 the limit itself does not exist. So if the limit of the function does not exist, no matter how you define your fx, you cannot remove this discontinuity. But you see at x is equal to 2, at x is equal to 2 the limit is existing. At x is equal to 2, limit x tends to 2 is, how much is the limit? 1. So if I suitably define my function as f of 2 is equal to 1, then what will happen? Then this discontinuity will be removed. So at x is equal to 2, the discontinuity is removable discontinuity. Now we will see at some properties of continuous function. If function f and g are continuous at a point say x is equal to c, then the following combinations are also continuous at x is equal to c. Like the sum of continuous function f plus g, that will also be continuous. Difference like f minus g, that will also be continuous. Constant multiple k times f will be continuous. Product will be continuous. Quotient will be continuous f by g, provided g of c is not equal to 0, because in that case this quotient will not be defined. Power is also continuous, and the root nth power of f, that is also continuous function, provided it is defined on an open interval containing c where n is a positive integer. There is another property of continuous function, that is called composite of continuous function. Suppose I have been given that f is continuous at c. So my function f, it is continuous at c. So I will, by mapping of this point c, I will reach at fc. Now there is another function g which is continuous at fc. Now this g is defined for this function g, the domain is range of f, then only you have composite functions. So this function g is continuous at fc. So effectively what will have, you will have, say, if the composite function is g of f, that will be continuous at c. For example, let me give you one example. Suppose you define your fx as fx is equal to x square and your function gx is equal to sin x. Now this x square is also a continuous function at any point. Similarly, sin x is also a continuous function at any point. So if I define my g of f, what will be g of f? It will be sine of f of x, that is sine of x square. So I can say that sine of x square is continuous at any point. Another very important theorem, that is limits of continuous function. If g is continuous at the point b and limit x tends to c fx is equal to b, then what I can say, if I have to find the limit of x tending to c g of fx, then I can write it as g is equal to z of b is equal to g limit x tends to c fx. In effect, what this theorem says, if you have been given a function g, which this function is continuous, and you have to find limit of this g at any point x tending to c, okay, and you have something inside this bracket, then this limit you can take inside the bracket because your g is continuous there. So if I have to find limit x tends to c f g n of fx, then what I will do, I will just take this limit operation inside the bracket and I will have is equal to g of limit x tends to c f of x. Now some examples based upon this theorem. Suppose I have to find what is limit x tends to pi by 2 cos of this whole thing. Now since cos is a continuous function, I can take this limit operation inside the bracket. So the limit, the x tends to pi by 2 cos of whole this thing will be cos of this limit. Now we take limit x tends to pi by 2, this 2x will become pi and this will become sin 2 pi, so this will become cos pi is equal to minus 1. Similarly, if I have to find limit x tends to 1 sin inverse this thing, I can take this limit operation inside this bracket. So it will be sin inverse limit x tends to 1 by 1 minus x by 1 minus x square. This all of you can very easily find out by cancelling the common factor 1 minus x. You will get sin inverse 1 by 2 equal to pi by 6, and we can do this thing because arc sine, that is sin inverse, is continuous function. Similarly, suppose I have to find limit x tends to 0 root of x plus 1 e to the power tan x. Then what I can do, first I will find limit of this thing into product e to the power limit. I can take this limit on power also, and why can I do this? Because exponential is also a continuous function. So this limit x tends to 0 tan x will be 0. So e to the power 0 will become 1, and this will also become 1. So the answer is 1.